Welcome to Applied Photophysics Higher Order Structure video series. In this video, we're going to dive into the topic of circular dichroism higher order structure comparisons, namely their applications, their use cases, and an overview of how they are performed, including a glimpse into the underlying mathematics. Subsequent videos in this series will cover specific case studies, practical considerations, and guidelines for data processing. Circular dichroism, or CD spectroscopy, is a powerful orthogonal technique in the biophysical toolbox. While methods like X-ray crystallography, NMR, and cryo-EM provide high-resolution structural insights, and techniques like ITC and SPR probe interactions, CD offers a unique perspective by detecting changes in structure and stability. Its rapid, label-free analysis makes it an essential complement to these methods, enabling a more comprehensive understanding of biomolecular properties. CD spectroscopy is widely used in academia and the biopharmaceutical industry to study biomolecules, particularly proteins and peptides. CD spectra provide valuable insights into both secondary and tertiary structure. Secondary structure information is derived from signals arising from peptide bonds that absorb in the far UV range, spanning approximately 180 to 260 nanometers, enabling the identification of structural elements such as alpha helices, beta sheets, turns, and random coils. Insight into tertiary structure is obtained from spectral contributions of aromatic amino acids, which absorb in the near UV range, spanning approximately 250 to 350 nanometers. Key chromophores include tryptophan, tyrosine, phenylalanine, and disulfide bonds. The near UV range can be considered a fingerprint region because its spectral profile is exquisitely dependent on the composition of aromatic residues and the conformation and environment of their side chains. Modern protein CD spectroscopy is most powerful for comparative analysis of secondary and tertiary structure, commonly referred to as higher order structure, or HOS comparisons. Examples include assessing batch-to-batch consistency in biotherapeutics, evaluating the effects of mutations, and studying the properties of charge variants or glycovariants to a parent protein. HOS analysis is also highly effective for studying the impact of formulation excipients, pH, and ionic strength on protein conformation. HOS comparisons have a wide range of applications and play a critical role at every stage of biotherapeutic development, from early-stage analytical assessments to late-stage quality control, from formulation development to force degradation, shelf stability assessments. Higher-order structure comparisons leverage both far and near UV wavelength ranges to enable statistically robust and quantifiable data analysis. When paired with a high-sensitivity instrument like the Chirscan Q100, featuring a temperature-controlled autosampler capable of high-fidelity 24/7 operation, these studies produce highly reproducible, quantitative results through a transparent and objective approach. Over the last decade, higher-order structure comparisons have been established as an essential tool to consolidate CD data and submissions for new biologics drug applications. Particularly in biosimilars development, HOS comparisons are indispensable to meet requirements by the FDA, EMA, and other regulatory bodies. The rationale for this guidance is to regulate and control the safety, quality, and efficacy of therapeutic agents available to the public. HOS comparisons are routinely used for assessment of HOS as a critical quality attribute of biopharmaceutical, antibody-based products to define a product's quality target product profile and to support totality of evidence and regulatory submission. So how do we carry out higher-order structure comparisons of biotherapeutics? At its core, an HOS comparison quantitatively evaluates whether any pair of spectra differ, and by extension, whether their underlying structural information is different. In this example, we want to determine whether aliquots of a Fab subjected to various stress conditions are structurally different. Detecting subtle differences between samples requires multiple independent replicates and robust statistical analysis. Even with precise overlays, many variations are too small to be discernible by eye. There are various approaches to HOS comparisons, and numerous spectral comparison methods are described in the literature. However, regardless of the HOS comparison method or application, all methods are mathematical approaches that have the same goal of yielding a single value as a measure of similarity for pairwise spectral comparisons. In this video, we will focus on the Weighted Spectral Difference, or WSD method, an HOS comparison method favored by many biopharmaceutical companies and regulatory authorities. Comparison of two spectra by the Weighted Spectral Difference method yields a single value, a WSD value in the same units as the spectrum, as a measure for their similarity according to a rather simple equation. A WSD value of 0 would imply that the compared spectra are identical. The larger the WSD value, the greater the difference between the compared spectra. Generally, an HOS comparison always requires a reference with which to compare. The reference, whether an innovator biologic, specific batch or lot, or wild-type protein, should be part of the same experiment and designated in advance of performing the calculations. To obtain the weighted spectral difference for the pairwise comparison of a reference spectrum with a sample spectrum, first, the sample spectrum is subtracted from the reference spectrum. The resulting difference spectrum, shown in blue, is then squared so that negative values cannot cancel out positive values. A wavelength-dependent weighting based on the reference is then applied to this squared difference. First, the absolute values of the reference are taken, again to account for negative signals. This weighting reduces the relative contribution of low signal regions where spectral variation stems mainly from noise. The absolute reference is then normalized by dividing through its average, shown in red, and the squared difference spectrum is multiplied with the normalized reference to obtain a weighted difference spectrum, illustrated here as the solid orange spectrum. Finally, the WSD value is obtained by calculating the average intensity of the weighted difference spectrum, illustrated as the dashed orange line, by summing over all data points, dividing by their total number, and taking the square root of the result. The preceding mathematical treatment provides one weighted spectral difference value for each pair of spectra. To enable statistical analysis and achieve objective, statistically validated results, it is necessary to acquire spectra from multiple independent replicates, typically at least 5 to 6 per sample. Each replicate is then subjected to pairwise comparison. In essence, HOS comparisons follow a two-step sequential process by first defining a quality range based on the reference replicates and subsequently comparing similarity values for the sample replicates to this quality range. In the first step, WSD values are calculated by comparing each reference replicate to the average of all other reference replicates, i.e., reference-reference comparisons. This step assesses the variability within the reference spectra and allows the establishment of a quality range. The quality range is typically defined as the mean WSD value plus or minus a multiple of the standard deviation calculated from the reference replicates. Commonly, the range is set to span between plus and minus 2 standard deviations. This quality range serves as an acceptance criterion, allowing the reference sample comparisons to undergo a quality range test. In the second step, weighted spectral difference values are calculated for the samples, i.e., reference sample comparisons. Each sample replicate is compared pairwise to the average of all reference replicates. The resulting WSD values can be plotted by sample on a graph alongside the established quality range. This allows for determining whether any sample differs from the reference. If the WSD values for enough sample replicates fall within the quality range, the sample is considered similar to the reference. Otherwise, it is deemed different. In this example, the tertiary structure of various biosimilar lots was found to significantly differ from that of the innovator biotherapeutic. To assess differences statistically, similarity values can further be subjected to a student's t-test that yields a p-value. P-values below 0.05 then indicate that observed differences are statistically significant. The prerequisite for conducting the higher order structure comparison studies described here is a CD system with exceptionally high sensitivity to allow detection of subtle spectral differences and high reproducibility to enable reliable statistical analysis. The Chiroscan Q100, with its large area avalanche photodiode detector and integrated automated liquid handler, is the only system in the market that can fulfill these requirements to the highest standard. We hope this first video in our higher order structure video series has been of value to you. Be sure to like and subscribe to our channel to be notified when new videos are released. For more information, including application notes, hardware and software support, and contact information, visit photophysics.com.